Right now within the instrumentation program in the second year, student teams are actively working on PID controlled processes. We are putting together this process here that you see using a toaster oven, an Allen-Bradley SLC500 PLC, and an Automation Direct Seymour HMI unit to make a temperature controlled process. We're using the toaster oven as the actual process. It's a standard toaster oven. We have done nothing to this except for drill a hole in the side through which we can insert an RTD. And if we take a look inside, you can see the RTD, the tip of it inside there for measuring the temperature. The PLC itself is an Allen-Bradley SLC500 unit, 4-slot with a 505 processor. We chose the 505 processor. We happen to have one donated from a local oil refinery, and it has Ethernet capability, and this Ethernet connection is going to be used to communicate with the HMI. So we're going to do that a little bit later. Currently the HMI is not powered up. We will have that powered up within the next week, and it will serve as the operator interface to the PLC. For right now though, we're just using the RS Logic software to talk to the PID control block inside the PLC. And speaking of that, we are using PID control, full PID control on this. And the way we're doing the control, since we don't have an analog device here to control on the oven, what we have is a discrete output on this DC source module that's sending a 24-volt DC signal to a solid-state relay mounted on the back of the panel. That solid-state relay then sends power to this receptacle which the oven is plugged into. The idea is it's pulsing the heating element of the oven on and off in order to modulate the amount of heat, the amount of energy going into it. You can see this on the front of the oven. You can see the power light turning on and off as that power is being modulated. And that frequency and that duty cycle is the same as what you see over here on channel 0 of that output card. If I pan back, you might be able to see both lights at the same time. That light on the oven right there, and that light on the output card right there. So they are in sync. So the DC output card drives a solid-state relay. Solid-state relay sends 120 volt AC to the plug, and that goes over here to the oven. And we chose a 1 second cycle time on the duty cycle there to be fast enough so the oven doesn't have enough time to physically warm up and cool down between the on and off portions of that cycle. So by pulsing it like this and varying the duty cycle of the pulse, we can control the amount of power sent to the oven, the amount of heat. So I'll demonstrate that over here. I'm going to take the PID control block in the program. I'm going to put it into manual mode. That way I get to tell what the output's going to be. I'm going to set the output right now to 0%. When I do that, we don't see any blinking here on the card. We don't see any light on the oven, neon light right there. There's no power going to it because we have a 0% duty cycle. If I type in a 25% duty cycle right there, what we're going to get is a 1 second square wave pulse that is on 1/4 of the time and off 3/4 of the time. So this is a 25% duty cycle. You can see it here as well. It's on for 1/4 of a second and off for 3/4 of a second. Back to here, I'm going to change this to a 50% duty cycle by entering 50 in the PID control output. And now our pulse width modulated signal is on for half the time, off for half the time. 1 second period means it's on for half a second, off for half a second. I come back over to here and enter a 75% output in the PID block. And now our pulse width modulated signal is on 3/4 of the time and off 1/4. So over here, on for 3/4 of a second, off for 1/4 of a second. So with increasing duty cycle, we're sending more heat energy into the oven. And here right now is 100%. We come over here to 100%. That light is on all the time. It means the solid state relay is being driven on all the time, power all the time, neon light in front of the oven all the time. So that's how we exert pulse width modulation control in this PLC program. So I can turn this back to 30% where it was before, throw it back into automatic mode, and now it's going to be controlling to a set point. I have a set point of 50%. Currently the process variable is 42%. This is on a scale of 0 to 500 degrees, and so 50% of 500 degrees is 250 degrees. 43% of 500 degrees, well, 40% of 500 would be 200, 3% more, It'd be about 15 degrees, so yeah, about 215 or so. So we are approaching our set point of 250 degrees, expressed in percent. Later on, when we get our HMI programmed here, what we're going to do is actually have graphs to show the process variable over time and show the output over time, so we can do more formal tuning of the PID control. We'll also be able to show the temperature in actual engineering units of degrees Fahrenheit. And speaking of measuring the temperature, we are doing that with an RTD through an RTD input card. This is a special analog input card to the PLC. It does not take in a 4 to 20 milliamp signal, as many analog cards do, but rather it directly takes in the RTD signal, and it powers up the RTD as well. It actually sends the current signal out to the RTD, measures the voltage drop across the RTD, and uses that to figure out the resistance of the RTD. And it scales it directly in engineering units, which is pretty cool. So we can take a look at the register inside the PLC's memory and actually read directly in degrees Fahrenheit. And that is our controlled oven process. Why are we doing this? Why are we putting an expensive PLC on a toaster oven? As usual, because we can.